Okay, it's time to finish up Module 10 in Part 2 here. We're still going to be talking about differences in means, but now we're going to discuss something called the matched pairs test, or sometimes called a matched samples test. In the first part of this module, we took independent random samples of gas prices as our example in Chicago and Hammond in order to compare their means. There's a different approach that can sometimes be used, called a matched samples or matched pairs approach. Probably the easiest way to explain the matched pairs approach is to just use an example. Suppose we want to compare prices of products sold at two grocery stores. We could go back to the first method and take independent random samples of items at the two stores, but a different way is to choose the exact same items at the two stores. That is, that's where the matching comes in. So suppose we've matched 7 items. We've got 7 products here, and we've got the exact same products at store 1 and store 2, and we've recorded their prices. What we're going to do now is calculate the sample difference in these prices, DI. That is, we're going to take price 1 minus price 2. $4.95 minus $4.50 is a difference of 45 cents, etc. The nice thing about this approach is now we've taken these two variables and we've pretty well condensed it to just one. It's going to be back very similar to doing statistical inference on a single variable. We'll have a little different notation as usual. Mu D is going to stand for the population mean difference between the prices at the two stores. So in other words, mu D represents mu1 minus mu2. Notice that if the two means are equal, if mu1 equals mu2, then mu D would be 0. Mu1 minus mu2 would be 0. That's going to be the most common hypothesis. We're just going to do a hypothesis test here, by the way. We could do a confidence interval, but we're just going to do the hypothesis test. Our test statistic, which should look a little familiar to you, is that you're going to take your sample mean d bar, you're going to subtract the hypothesized mean, which is usually 0, and divide by the standard deviation of the differences divided by the square root of n. Turns out that this is a t-statistic with n minus 1 degrees of freedom. I ask you over here, does this formula look familiar to you? And it should, because it's basically the same formula that we had back in Module 9 when we were doing hypothesis tests on a single mean, just the notation is a little different. Instead of x bar, we now have d bar. You subtract the hypothesized mean. And instead of s over the square root of n, we'll call it sd to illustrate the fact that it's the standard deviation of the differences. Now to use this formula in our current example, we're going to have to calculate d bar and sd. That is, we're going to have to go back to our data right here, and these are the differences. We're going to have to take those 7 differences and calculate the mean of them and calculate the standard deviation. Before we get to that, technically we should really have a sample size of at least 30 for the central limit theorem to apply as always. Or, as in our present example where the sample size is smaller, we only have a sample size of 7 here, we would need to assume that the populations we're sampling from are approximately normal in shape. So, let's get back to our problem. Does our sample data indicate a difference in the mean prices at the two stores? Suppose we want to test that hypothesis at a 5% level of significance. Our hypotheses are going to look like this. Notice the problem just said, is there any difference in the mean prices at all? So that indicates a two-sided test. Is mu d 0, which would mean the two means are the same, or is mu d not 0, which would mean the two means are not the same? We choose a level of significance, which I'm going to choose here to be 0.05 or 5%. As I said a minute ago, we're going to have to calculate the sample mean and standard deviation in order to get this test statistic. If you do that here, remember the sample mean, you just sum the numbers, divide by n, you should get a sample mean difference of 15 cents. And if you calculate the standard deviation, and I believe I used a calculator to get this, you'll get a standard deviation of 0.178, or that would be between 17 and 18 cents. Now we can calculate our test statistic. Take 0.15, your sample mean, subtract the hypothesized difference, which is 0, over the standard deviation over the square root of your sample size. And you should get a calculated t-statistic of 2.23. If we want to use the critical value approach, we'll have to go to the t-distribution and get our critical t-values. With 6 degrees of freedom, n minus 1, and alpha over 2 is 0.025 since we wanted a 5% alpha level. You just go to your t-table and you will get critical t-values of 2.447 or negative 2.447. So we will reject the null hypothesis if we get a t-value above 2.447 or below negative 2.447. However, since our t-value was only 2.23, that's less than 2.447, we are unable to reject the null hypothesis. And since we're unable to reject the null, that means we are unable to state that there's a difference in the mean prices at the two stores. Graphically, using the t-distribution here with 6 degrees of freedom, our critical values, 2.447 in the right end, negative 2.447 in the left end. Our t-value of 2.23 did not fall in either rejection region. So we were unable to reject the null. Again, you have a choice. You could use the p-value approach. Remember, with the p-value approach, we always reject the null if the p-value is less than our alpha level, which in this case is 5%. Technically, the p-value would be 2 times the probability of getting a t-value above 2.23. That is, 2.23 was our calculated t. You find the area above it and you double it since it was a two-sided test. On a calculator, the exact p-value is 0.0672. If you were using a table of t-distribution values, the best you could come is to specify a range that it's somewhere between 0.05 and 0.10. Again, we'll have the same decision and conclusion as before. Since the p-value is less than alpha, we're unable to reject the null, and therefore we are unable to say there's a difference in the mean prices at the two stores. By the way, if you wanted to do this test on your calculator, you could go back to Module 9 and it would be exactly the same as when we did the t-test at that time. Because as I said, you've condensed the two variables down to one, so you're really doing a hypothesis on that one variable, the differences. Graphically, here's a way of looking at the p-value approach. Remember again, with the p-value approach, you're comparing two probabilities here. One is the alpha level, which was 0.05. Half of it in this end of the distribution, half over here. 1/2 the p-value, the probability above 2.23, which again from my calculator was 0.0336, double that for the other side. In this case, the p-value is larger than alpha, and therefore we are unable to reject the null hypothesis. And that's all we're going to do in Module 10. And we're going to move on to our next topic, which will be simple linear regression.